in class today came up with this concept and this idea of work being done. And work, we said, was a measure and a transfer of energy by a force. So if a force pushes an object and the object decides to move, then we can say that work is done. And work there is really just force multiplied by the displacement. And units you can see there are newtons multiplied by meters, which we now call joules. Or if you're using the English units, we can use foot-pounds of work done. So we did all these scenarios in class. Make sure you have those sketched out somewhere in your notes. If you don't have them, sketch them and make sure you remember which scenarios gave us work done and which ones did not, which ones gave us positive work, which ones gave us negative work. And here's the recap of those. The positive work was done when the force and the displacement were in the same direction. That was positive work done. Negative work is when you get the force and displacement 180 degrees apart in opposite directions. And if the force and displacement were perpendicular to each other, then no work is done. And so we can write that as work is force times the cosine of theta times the displacement that you've done. What we're going to be looking for in scenarios is the net work done, the total work done by all the forces on the object. And if the net work adds up to something, we'll see a change in our situation. Which leads us to what we call the work-energy theorem. And the work-energy theorem says that if work is done by an object, the result is a change in that object's motion. Forces do the same thing, but we saw that today the force was changing with our spring force. So our spring force was changing in our scenarios. If that cart was stretched out very, very far, it experienced a certain spring force back. But as the spring starts collapsing, the spring force becomes weaker, which means our acceleration is weaker, which means we don't have a constant acceleration like we've had in all of our other units. So with a changing force and a changing acceleration, energy is a better way to describe how things actually change their motion. So what does it mean to have energy? Well, if an object has energy, it has the ability to do work. It sounds like I've just said the same thing in reverse, and I kind of did. If you do work on an object, you will change the object's motion, or you'll change its energy. And if something has energy, then that object has the ability to push things a certain distance and do work for us. So the three types of energy that we'll deal with in each of the units here will be kinetic energy, potential energy, and thermal energy. The way I like to think about energy is I like to think about energy as money, something that you can actually move around from place to place. And if you think of the quickest way to move money around, it's through cash. And I can hand them $100 and they're $100 richer, or they have 100 units of energy more if I'm equating energy to money. So for kinetic energy, think of cash, quick moving, fluid amounts of money, fluid amounts of energy. With potential energy. Potential is energy you have, but you don't need to use it. It's stored up in a certain spot. And we'll deal with that all in the next chapter. But the way I think of potential energy in terms of money would be a savings account. So I have money in my savings account. I can use it. I have the potential to turn it into cash, but I don't have to. And the energy of the system would be how much total energy do I have between my cash and my savings? How much total do I have for whatever system I look at? If the system is just myself, I just look at my savings plus my cash. If I'm talking about all the people in Penn Trafford, I'd have to look at everyone's amount of kinetic energy and everyone's amount of potential energy. So what causes changes in kinetic energy? It's force. Force makes things accelerate, and if things start to accelerate, that means their motion is changing. That means the object is moving faster or slower. We know now that work is force times displacement, so I can substitute in ma for my force, and I get mass times acceleration times displacement. And using our kinematics, let's go back and see if we can solve for an acceleration multiplied by a displacement. So looking back at our kinematics equations, you can see that we have this one, and right in the equation here is my 2ax. I just need ax, so if I do some algebra, you end up with the acceleration multiplied by the displacement should be vf squared minus vo squared over 2. So I'm going to sub that back in to my equation for work, and work's going to be mass multiplied by VF squared minus VO squared all over 2. I can expand that mass into both of those equations there, and what you get is that work changes an object's kinetic energy. If work is done, an object's kinetic energy must change. And kinetic energy will be the formula of 1/2 mv squared, which we get that from, here's our 1/2, here's our mass, multiplied by each of the v squareds. My VF squared minus my VO squared will give you changes in kinetic energy. In this scenario, we're trying to see if work is done. And if you see the displacements to the right and the forces to the right, then yes, positive work is done in that first top scenario. In the second scenario, work is still done because the box is still moving to the right with a force applied. That force is applied at an angle, so technically there's an x component and a y component to the force. The only one that's going to cause work to be done is that x piece. Cosine component of the force multiplied by the displacement will give me the amount of work done. A couple of you were asking for examples of why we use dot products and where they apply. Well, here's our example right here. The length that this box is traveling is 4 meters in the I direction, 3 meters in the J direction. So there's a couple ways that I can do this, and I'm going to show you that any way you go about this, you should end up with the same amount of work done. So if we look at this scenario, we've got a 3, 4, 5 triangle here. So that angle comes out to about 36.7 degrees. So if I want to go at this, I'm going to go at it a couple different ways for you, and I'm going to show you that no matter what we do, we get the same thing. Let's go with the definition of work. Work, that's force dotted with a displacement. So I'm taking a force vector, I'm multiplying it by a displacement vector, and I'm going to get a scalar quantity out of here and see if I get positive or negative work done. So if you look at what I've got here, I've got force is 100 newtons in the I, and length 4 in the I and 3 in the J. So if I follow my rules for dot product says that I must take the x component of my force multiplied by the x displacement, and I'm going to add that to the y component of my force multiplied by the y displacement. And the nice thing for us is the force is only in the x direction. I have 100I and 4I. I dot I actually gives us a number. I dot J gives us nothing. So this whole quantity doesn't matter, and you've got 100 newtons times 4 meters, or you end up with 400 newton meters, or 400 joules. So there's your answer. Work was done here. That means the box, if it was at rest at the beginning, is now moving as it reaches the top because positive work was done. Let's try that another way. Instead of actually doing just the dot product, the other half of that equation was to take the magnitude of the force multiplied by the magnitude of the displacement and multiplied by the cosine of the angle between them. In this case, that angle is theta. Phi is just another angle that we could call it. So if I look at that then, I need to find the magnitude of the force vector. Well, that's 100 squared plus a 0 squared. Square root gives me that the force vector is still 100 newtons. The displacement vector is going to be 4 squared in the I direction plus 3 squared in the J direction. That gives me 25. When I add those two together, square root of 25 is 5. So I get 5 meters. So 100 times 5 is 500. However, we've got to multiply by the angle that they are separated, and the angle is 36.7 degrees. So put that in your calculator, and you end up with 400 joules. So I can do the dot product if I'm given the IJ components. I can break this up into its components here and do magnitude of force and magnitude of displacement multiplied by the cosine, and I get 400 joules. Or let's talk about how much force is in the direction of displacement. So for this one, I'm going to move the force vector right here. And the question would be, how much force is in the direction of displacement? So I'd be asking, how much of that force vector actually pushes us up the hill? Well, if I wanted to find that component, I'd be looking for the force that's parallel with the plane. And in this case, to calculate the work, it'd be force times the cosine of theta to give me that force that is actually pointing up the hill. I'm going to multiply that by the distance that I'm traveling in that plane. Because remember, work is only done if the force and displacement are in the same direction. It's going to be 5 meters. Force times cosine comes out to about 80 newtons times 5 gives you 400 joules. So if you just want to look at the force that's pointing up the hill, that's another way of calculating the work. A third way of calculating the work would be saying, okay, here's my force vector again, separated by that angle theta. How much of the displacement is in the force direction? So how much of this blue vector is actually pointing in the same direction as my force? So what I have to do is find the displacement that is parallel to the plane. If I wanted to find the parallel r vector, I'm going to take r cosine. I'm going to take r cosine of theta. R being this length vector that goes up and down the plane, so that's 5 times the cosine of 36.7 degrees, comes out to about 4 meters. So now that I have that this is the parallel displacement component, I just have to multiply that by the force that's in that direction. Is force times r parallel comes out to 100 newtons multiplied by 4 meters, which again gives us 400 joules of work. So I just showed you 4 different ways to solve this problem if I wanted to solve for the net work done. And this is what we showed you with the race day today. When we have a force versus displacement graph, the area under the curve is what's going to tell us how an object's going to move. The area under the curve for a force displacement graph is the work done, is the joules of energy imparted on an object. Whether that is a flat line and you get a nice steady amount of work done. If the force changes over a distance, you can see in that bottom corner I can add those 2 areas together to get the total net work done. If the line for my force would be negative with a positive displacement, this area down here would give me the negative work done over the scenario. And if negative work is done, we're losing energy out of the system. So you got to look at what side of the graph you're dealing with. Are we dealing with positive areas or negative areas? And sometimes the force doesn't exactly match up with your displacement. It may not be a steady force. It might be a changing force as you're displaced. So in that case, we've got to look at all those tiny little areas underneath that force curve so that we can figure out the total work done for this scenario. So what that means is that we're going to have to integrate. Because if there's a varying force, like our springs were today, the further you stretch the spring, the more energy you put into the spring, the more work done. So we're going to have to integrate if our areas aren't nice, perfect curves. Looking at the spring, if I move the box to the right, the spring force is going to fight back and try to pull the object back to that unstretched length. If I compress it like I do at the bottom, then the force is going to be in the positive direction and give me positive work done. So let's show a derivation of what happens if we have to add up and integrate all of our work done over the entire distance. So if we want to add up the work done by a spring, what we're going to have to do is integrate the force times the displacement. And the reason I have to integrate is because the force is changing every single second as I move from my initial to my final point. So the way we can put that in is I can put in my spring force equation, which comes out to the integral of negative kx dx from my initial point to my final point. I can pull out anything that's constant here, which is the negative k. And now I'm going to integrate x dx. The integration of x dx is x squared over 2. So that's negative k multiplied by x squared over 2. And now you've got to put in your 2 bounds, your final point and your initial point. Your final point in, you get negative kx final squared over 2 minus negative kx initial squared all over 2. That is the work done by the spring. So if we put this into practice here, you could say, all right, if the initial stretch on the spring is 0, that would wipe out this piece. And the final stretch on the spring could be 5 centimeters. So 5 centimeters squared multiplied by the K constant, the spring constant for that spring, divided by 2, gives you a negative amount of work done by the spring. Why is it a negative amount of work done? Because if you look at that middle scenario here, as the displacement is in the positive direction, the force is in the negative direction. So the spring is doing negative work. The person that's doing positive work here is you. You're applying that force forward, and you're making the spring stretch in a forward direction. So you're pouring energy into the spring while the spring has negative work done against it. It does not want to be stretched. Same thing could happen if I pushed the spring backwards. Since it's 1/2 kx squared for the work done by a spring, no matter if I have positive or negative displacements, you're going to see that the spring is going to have negative work done against it. It's pushing positive as the block moves backwards. So if you are the one stretching the spring, then you're going to have positive work done by the person and negative work done by the spring. However, if you let this go, if you let the object go in the middle scenario here, and you let the spring force bring the object backwards, so if the displacement is back towards the 0 point, now the spring is doing positive work. And if this object was initially at rest, by the time it reaches that midpoint, it's going to be moving pretty quickly. So it's going to have a velocity because the spring has now done positive work. If you want to know the magnitude of the energy that was sitting inside that spring, the work done by a spring, or the energy in a spring, can be simply found by doing 1/2 kx squared. X being the stretch length, K being the spring constant. That's how you can get the energy stored in a spring. And the energy stored in a spring will turn into work that the spring does to increase the speed of that object.